I'm going to talk a bit about volume rendering and hardware acceleration. So first, volume rendering is something that is very popular in computer graphics. It can be used for data visualization or representing computer-aided design scene, but also for typical oil rendering with rendering of cloud, smoke, and other type of effects. There is many ways to do so. One of them is marching. There is also many approach to marching and representation of data. One of them is implicit surfaces. So the idea is that you represent your surface by a function or a signed distance field or procedural noise. It's usually quite costly to evaluate, but it has the advantages of having a very low memory cost, as the functions are typically easier to store than plain voxel or triangles. However, it's quite difficult to animate, and it has a poor workload balancing, and by that I mean that usually all the work is done by a single shading stage, usually a fragment shader, but it also can be a compute shader. When it comes to voxel, it's a bit similar. It's an explicit representation, as my colleague presented just before. It's quite easy to evaluate, but it requires complex memory management. But it's also very hard to animate. And once again, fragment shader or compute shader is doing all the work. And we don't really use much of the hardware accelerated feature of the GPU there. You can also try to accelerate that using acceleration structure. So here I took the example of bounding volume hierarchy. It limits the computational cost using pre-computed hierarchy. But the hierarchy evaluation is not free. It's quite hard to animate because you have to reconstruct your hierarchy if objects move too much. And also, once again, the hierarchy is evaluated by the fragment shader or the compute shader. And one other type of method I wanted to look at is surface-based volume rendering. So by that I mean all the peeling approach. So basically you render multiple times your scene, and each time you store the fragment you first meet, and then you do it once again by ignoring the fragment you already met. And it helps you create depth intervals that you can reuse afterward to do your volume rendering. Problem of that is that you have to store multiple frame buffer, which can be quite costly. It does not always work with overlapping geometry. It can create weird artifacts. And however, this has a more balanced workload because we are using the rasterizer, the fragment shader, vertex shader, and everything. So in summary, I showed two types of approach: marching-based and surface-based. So marching-based has the advantages of being low memory. However, it's high computational cost, poor workload balancing, and very hard to animate. In comparison, surface-based are very low computational cost. They are quite good at workload balancing and easy to animate. So if we focus on this type of approach, we can see that all the advantages come from the fact that we are using hardware accelerated primitives there. And the only drawback comes from the fact that we have to reconstruct all the depth interval in the post-process. So the question I wanted to ask during this work was, can we use volumetric hardware accelerated primitive in the rasterization pipeline? If we look at what we have access to, we have access to vertices, edges, and triangle, but nothing in 3D. And ideally, we would like to have access to tetrahedron, but it's not the case. And one of the reasons why this is not the case is because when you look at simpler primitive, its screen space projection is always a fragment with a fragment coordinate, a depth, and all the attributes that come with it. And then this result is sent to the fragment shader that does its work. In comparison, if we were to do the same kind of operation on 3D primitives, it would create an interval because we have both a front and back face with a single fragment coordinate still, but two depths basically, and then pairs of attributes after that. And if we were to dream about this ideal volumetric pipeline, it would take as an input tetrahedron with vertices and indices as we do typically for surfaces. This tetrahedron will be sent to the rasterizer, and then all of that will be solved by an interval shader that will replace the fragment shader. But as I said, we don't have access to tetrahedron. So question is, can we bypass this? So my hypothesis when doing this work was maybe you can use an early stage fragment to encode the tetrahedron such that the rasterizer be coerced into computing this projection that we want, and then getting our result in a fragment shader. So typically, early stage of the pipeline only handle hardware-accelerated primitive. However, recently, mesh shaders were added to the pipeline, and they can handle arbitrary geometry and in a very complex way. So maybe there is something to do there. But to understand how we can coerce the rasterizer into computing what we need to understand how it works. So first, let's say we try to rasterize a single triangle. The rasterizer will, for every pixel on screen, will try to decompose it into screen space barycentric coordinates that represent the position of the point with respect to the vertices. And then using that, it will recompute the depth using a very similar equation here, but just using 1 over the depth. So now that we know that, can we actually generate depth intervals? To understand how it works, we have to focus on a much more simple case than tetrahedron. And this case is what I call the prismoid. So it's just 2 triangles that project exactly on the same pixel in screen. So here you have 2 representations, one in projected space and one in camera space. For the remainder of this presentation, I will focus on the projected space as it simplifies the equation quite a bit. So as we have a couple of points that are equal in screen space, we can define these equalities there. And using that, we can reapply the same equation that would apply the rasterizer to both triangles. And we can see that actually we can use the same set of screen space barycentric coordinates to represent the same point on both triangles here. And so by just following the same method, we can compute 2 depths using the same set of barycentric coordinates and with just this equation here. So now the question is, how can we force the rasterizer to compute these 2 depths, and how can we have our results? Well, the solution is this one. You encode your 2 triangles as a single one, which will be used as a proxy, and you just encode x and y for the position, and you leave z to 0. And this will force the rasterizer to use screen space barycentric coordinates to interpolate vertices attributes. And then you just set up your vertices attribute as 1 over the depth of the 2 points, and then once the rasterizer will do the attribute interpolation, it will recompute these 2 depths. Finally, when you arrive in the fragment shader, each fragment shader invocation will receive 2 depths, so 1 over the depth of the front faces and the depth of the back faces of this peculiar shape. So now we have a big problem. Not everything is made of prismoid. And so now I'm going to explain how we can generalize that to tetrahedron. So to generalize that to tetrahedron, we have to reformulate a bit what we want as a properties for our mesh. So basically, we want to remesh the tetrahedron such that for each front faces, we have exactly 1 back faces. And to do so, actually, it's not that difficult. You have to separate the front and back faces, and then you have to recombine them in a merging operation that will create new vertices, new edges, and new triangle. You can find more information about this merging operation in the article. And actually, for the tetrahedron, it can be solved analytically, and there is only 2 cases. One case is where the tetrahedron presents as a footprint of a triangle in screen space, and in this case, you can only create 3 prismoids. And one other case where it presents as a quad in screen space, and then you have to create 4 prismoids here and 4 triangle proxy. And then you encode your geometry as I mentioned earlier for the prismoid, so x and y, and that's z to 0. And then you encode the front faces depth and the back faces depth. Finally, if we summarize our pipeline, as an input, we have vertices and indices that represent the tetrahedron. Then we have the mesh shaders that apply transformation, animation, and then encode the tetrahedron in a way such that the rasterizer will be coerced into solving the screen space projection of the tetrahedron for us. Finally, the fragment shader receives the depth intervals, so the depth of the front and back faces, and can do its shading in this band. So it works for a single tetrahedron, but it also works for an arbitrary number of tetrahedrons. And now if we focus a bit on what's happening in the fragment shader, so if we check this very simple scene, so we have 3 tetrahedrons, it's a cut view here. What we have is for each pixel, we trace an array, and we can see here that we have 3 intervals appearing. And these 3 intervals will be shaded separately in 3 different invocations of the fragment shader. And the fragment shader can compute optical depths or remarching within each of these intervals. And finally, results are merged by the blending stage or by the depth buffer stage. And what's interesting with this method is that if you have, for example, if you are doing, for example, a remarching operation, you may be aware of that remarching can be quite costly, mainly due to grazing rays. And here, in this case, for a single array, it will be divided in 3 separate intervals. And here, the grazing part of the array will be solved in a separate fragment invocation than the other parts. So it will reduce a bit the computational toll here. So now let's have a look at some results. So here are the 2 results I already showed. So here you can see the wireframe and the optical depths computed in a single pass of computation. But it can be also used for more complex objects, such as this one here. So here we can see we have a crystal that is rendered. And we can see that we have many overlapping parts in screen space that are correctly rendered in a single place while being transparent. Our method actually supports using multi-channel optical depths. So if you want to render complex objects, so here you have 1 color per tetrahedron, and then you can easily compute the transmittancy, and you can mix that with of map or any other effect you want. Right. So our methods support animation and intersecting geometry. So here you have an example of a complex system where the PAL is rotating, and then we create an exploded view of that. All of that is done in a single pass of rendering here. And we don't have to reconstruct any acceleration structure, as we are using just plain old tetrahedron there. Also, I didn't mention that, but by a clipping operation, we are able to put the camera even inside of the object without having many issues here. It costs a bit more, but it's doable. And finally, I mentioned earlier that we can do marching with our method. Here is an example. So I didn't put the video because encoding was a bit shaky on this one. So here you have 10,000 asteroids that are computed using an hypertexture each. And each of them is bounded by a tetrahedron, and so we compute each asteroid within the bound of the tetrahedron here. So here I put a summary of the performances of our method. So we can see that even with a very large number of tetrahedrons, such as the jet engine I showed, we remain real time, and even more than that, while being rendered in 4K on a RTX 4080. So finally, if we summarize, we proposed a tetrahedron rasterization method that can do single pass accurate transparent rendering. It can also be used for unordered volume rendering that support animation without needing to reconstruct any acceleration structure. Currently, this only works for unordered volume rendering, as intervals are solved separately and then blended just using the blending phase. But it could be potentially solved in future work using a peeling-like method, for example. Another limitation is that we only handle 1 tetrahedron per work group in the mesh shader at the moment. This might be just due to our implementation, as we do not yet have access to meshlet for tetrahedron that we have for surfaces. And so loading multiple tetrahedron might have had an issue while testing. Finally, we do not support per vertex attributes interpolation in the rasterizer. So I mentioned that we put z to 0 while encoding our tetrahedron, and this prevents us from doing correct interpolation of UV or texture code or normal or other stuff. So it might be solvable in the future by computing it in the fragment shader, for example, but it's still not really looking like that. And finally, I mentioned animation. I only showed here animation, rigid animation, mainly due to the fact that tet mesh with animation weights are hard to find. And so I was not able to test if it was working or not. But there is no theoretical reason for it to not work with animation weight. So that's it for me. All the source, here I put the link to the source of much of the example I showed. If you have any question, just ask them.
Questions for Thibault?
Yes.
I'm not sure if I missed it, but how do you obtain the tetrahedrons, for example, for this bunny? Where do you get the tetrahedrons from?
Oh, so the question is about how do we get tetrahedron meshes? I just use TetGen. Okay.
So I noticed in your results the kind of the frame rates weren't linearly, we're not in line with the number of tets. So why were some kind of higher tet models actually faster than the lower tet models?
Okay, so there is two things. I separated asteroids there. It used less tets, but each tet represents a marching invocation, so it's a bit more costly. And for the rest, it's a bit hard to know exactly why. One of our hypotheses is that we tend to, in some cases, saturate the blending phase, because usually we just emit 1 or, let's say, 10 fragments per pixel at the end. But here, with the number of tetrahedron, we have much more fragments per pixel to solve and to blend at the end. So it might be just that, but I'm not actually sure of the reason why here.
Any other questions? All right, let's thank Thibault again.